Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing a very important class of compounds called transition metal carbide uh, complexes, and we have been looking at their preparation properties and reactivity studies. So these transition metal carbynes are multiply bonded metal carbon species where you have sigma and 2 pi bonds attached to transition metals. Now, most of the synthetic strategy that we have discussed about preparing these transition metal carbine complexes involve construction of this carbonic triple bond from the corresponding transition metal carbene complexes. So most of the strategies involve conversions of transition metal carbene complexes to the corresponding transition metal carbine complexes. These are carbene complexes and these are carbine complexes. And what we had seen that the methods which were available for preparing these transition metal carbene complexes are also effective for preparing the transition metal carbine complexes, and hence there are a large number of methods which are available for synthesizing these complexes. We have also seen the spectroscopic techniques or characterization techniques that are often in place for characterizing these complexes that involve X-ray diffraction studies, as well as NMR, both proton and 13C, IR, Raman spectroscopy, and most of these are equally available for characterizing both of these carbene and carbine moieties bound to transition metals. Now, with that in the backdrop, we were discussing about various characterization of carbine moiety, including that of X-ray diffraction studies. X-ray diffraction is a very powerful method which gives direct measure of the bond lengths and bond distances, and what has been found that transition metal carbene bonds as well as transition metal carbine bonds shorter than that of the transition metal CO bonds. So let me illustrate that like T M C C A R B Y N A. This bond length is shorter than transition metal CO bond length. So that really indicates that this is more strongly bonded to that of transition metal carbine. And similarly, transition metal carbene bond length is shorter than transition metal carbon, let's say methyl bond length. So what really one can see that this is partially double bond character and this is partially even triple bond character. So with this backdrop, we are going to take up a few more examples of transition carbine complexes, particularly with respect to their characterization using X-ray diffraction. With regard to the existing examples of structurally characterized metal carbine complexes, one interesting examples that come to the fore is that of a tungsten carbine complex of the formula given below. So, structurally characterized example example of a tungsten carbine complex having the formula DNP tungsten CH2C Me3 CHC Me3 CC Me3. Now what is interesting about this compound is that it contains tungsten carbon single bond, it contains tungsten that is with respect to tungsten CH2C Me3 bond. It contains a tungsten carbon double bond, which is given by tungsten double bond CH Me3, and it also contains a tungsten carbon triple bond, and it's given by tungsten CCM3. So what we see that this is a very interesting example where in the same molecule 3 different bond length exists, and the molecule is given by CME3 CH2 CME3 CH CME3 E. So this is this DNP ligand, and as far the bond lengths are concerned, this tungsten carbon single bond is about 225 picometer. Tungsten carbon double bond is about 194 picometer, and tungsten carbon triple bond is 178 picometer. So we see that how the tungsten carbon bond decreases as one goes to single bond to double bond to triple bond, starting from 225 to 194 to 178 picometer. And this angle is also not linear. It is slightly deviated from this 180 degrees, which is supposed to be the linear angle, and it comes at around 175 degrees. To sp2, which is supposed to be 120, this is about 150 degrees, and the sp3 ones, which is a single bond, that is about 124 degrees. We see that 3 different bond lengths and the bond angle for this structurally characterized tungsten complex, which contain all the single bond, double bond, triple bond moieties. This is a very interesting example from that perspective. Now we're going to sort of look at the carbene tungsten metal interaction. We're going to look this perspective of tungsten carbene tungsten metal interactions and see how the interaction of carbine moiety with tungsten metal vary with that of carbenic moiety with tungsten metals. So we're going to sort of look at tungsten metal carbene interaction with from the perspectives of the carbenic bonds. Now, as let us start with carbenes. Now, as in the carbenes, we saw the carbenes are generally sp2 hybridized, and they had two systems. Okay. So, let us look at transition metal carbene interactions. Particularly, we are going to look at try to understand transition metal carbene interaction with respect to transition metal carbene interaction. So, to start with, let us sort of look at transition metal carbene frontier orbitals that are involved in interaction with their carbene complexes. So, as for the transition metal carbenes, what we saw that there was a sp2 carbon center which had a sp2 lobe and a empty pz orbital, and this sp2 lobe had a lone pair that is for Fischer carbene. This was a singlet carbene, whereas for the Strock ones it was a triplet carbene, so this was in a triplet spin state, and these were for carbenes. The carbenic moiety sort of looked like this in case of the Strock and the Fischer carbenes. And as for the carbene, where the metal is in, where the carbon is in sp hybridized state, where this is Py and this is Pz orbital and this is Sp orbital. Unlike the Sp2 over here, Sp2 over here in carbene it is a Sp orbital over here. Now, carbene also are of two types. One is a doublet carbene which is a Fischer carbene, where the Sp orbital has 2 electrons and the Pz orbital has 1 electron, and Strock carbene which is so this is the Pz orbital, this is the Py orbital and this is the Sp orbital. In the Strock carbene, all of this is contains one unpaired electron. So, this is in quartet spin state and these are called Strock carbene. So, here too what we see that Cr carbenic moiety exists in spin state which is doublet and quartet. Now, if one were to compare the reactivity or the fragment orbital of the carbene and the carbene, then one sees that all the 4 spin states are covered, starting from singlet, which is a Fischer carbene, then a doublet becomes Fischer carbine, then a triplet, which is a Strock carbene, then a quartet, which is Strock carbine. Also, what is important over here to realize is the fact that in Fischer carbene, where the sp2 orbital was occupied and the pz was vacant. Similarly, in the Fischer carbine case, sp2 is occupied, pz is half filled and py is completely empty. And similarly, for the triplet state in the Strock carbene, one can see that both the sp2 and the pz orbitals are half filled, as well as in the quartet Strock carbine case, both sp, pz and py, each of them are singly filled. So, this provides overall perspective of the carbenic as well as carbinic moieties and their electronic structure, and how they form the basis for interaction with the transition metal, and how that their reactivity would vary as to their interaction with the transition metal. So, with that we are going to sort of take a bit more, we are going to look a bit more in details about how this kind of metal carbine interaction happens. To begin with, we are going to restrict ourselves to this Fischer carbine moiety, and then we are going to take a look at the Strock carbine moiety. Now, as we had seen in metal carbene organometallic compounds, that there are two kinds of interaction called ligand to metal or metal to ligand, and similarly for carbine too, these metal ligand and ligand to metal interactions predominate and they play their own assigned role. So, let us start with Fischer carbine. Complexes, for example, Fischer carbine has carbon sp hybridized interacting with a metal. So, this is the sp pz py orbital, and that interacting with a metal orbital of metal d sigma symmetry, metal d sigma, and this being filled, there is a net electron donation which happens from sp to the empty metal orbital. So, this is filled and this is empty, and this ligand to metal sigma interaction. The next set of interaction is between half filled metal interacting with half filled carbon pz orbital. So, in this case the metal so, this is a pz orbital for clarity purpose, the sp orbital is not being shown over here, interacting with a metal d type, d pi type orbital. and in this case this singly filled orbital interacting with singly filled. So, this is the interaction which is sharing that happens between this d orbital and this p orbital. So, this is half filled and half filled interaction. So, this can be represented as transition metal to ligand pi interaction. So, this is a p y orbital, p z orbital, and the metal with having filled orbital. So, this is metal orbital having d pi symmetry, and here the interaction is between the filled with empty p y orbital. So, here this d orbital d pi orbital is filled and this p y orbital is empty, and that the interaction takes place between this and this p y, and this interaction is from metal to the ligand filled to empty. So, this can be designated as transition metal to ligand pi interaction. So, this is half filled, there is no arrow in the bond, this is filled to empty, there is arrow designating how the coordinative bond is happening, and this is empty to filled, and here. So, first one is sigma, second one is pi, and third one is a dative pi type interaction. So, what is seen over here, that in Fischer Carbyne species that the carbon is sp hybridized, and then there are two p type orbital, one is pz and py. Py remains vacant and pz is half filled, that when interacts with the metal d sigma orbital of sigma symmetry, then there is ligand to metal sigma donation as seen over here, as well as there is a d pi orbital of a metal interacting partially filled half filled d pi orbital of a metal interacting with the partially filled p z orbital of the carbonic moiety, and this is so called a half filled interaction. And then we have this the metal filled orbital interacting with an empty p y orbital, and this is filled to empty transition metal to ligand pi back donation. So, with that what we have learned today is the fact that transition metal carbynes are a very interesting pair of compounds. We started off with a structurally characterized example of a tungsten complex, where all the three forms of metal carbon bond, whereas metal carbon single bond as well as metal carbene double bond as well as metal carbine triple bond, all have been stabilized on this tungsten structurally characterized complex. And what we saw, that this bond length shortened with the increase in multiple bonding character, and that the single bond as expected was the longest, whereas the triple bond was the shortest, and the double bond being the intermediate one. And also we have seen that depending on the change in hybridization of the carbon from sp3 in a single bond to sp2 in a double bond to sp in a triple bond, the angle at the carbon moiety is changed from being linear to being bent, depending on their hybridization, which was sort of expected. We have also looked at the spin states of these Carbyne moieties, and what we had seen that Carbynes too can be classified as Fischer and Schrock type, with the Fischer type Carbynes being doublet, as well as the Schrock one being quadrate. So, what this brings us is the fact that overall all the spin species are covered if we compare the spin states of the carbenic as well as Carbyne moiety. So, from Fischer carbene being singlet, whereas Fischer carbine being doublet, and Schrock carbene being triplet, and Schrock carbine being quadrate. So, we have looked at the distribution of the electrons in the frontier valence orbital of this Carbyne fragment. Further on, we have also looked at how the interaction occurs between the Carbyne fragment in the doublet spin state along with the metal orbitals, and what we saw that these Fischer Carbyne interactions are of three types. The first one is a filled carbon sp orbital donating electron to the empty d sigma orbital of appropriate symmetry on the metal. So, this is ligand to metal sigma dative coordinate donation. The next one of the interaction that we see is a field covalent interaction involving half filled d pi orbital of metal interacting with half filled pz orbital of the sp hybridized carbinic fragment. And the last of the interaction we saw was this filled metal d pi orbital interacting with empty py orbital of the carbonic fragment. So, Fischer Carbyne type interaction consists of one Carbyne to transition metal sigma donation, another pi interaction between covalent pi interaction between transition metal and the carbonic fragment, and the last one transition metal to carbonic pi back donation in the carbonic fragment. So, with this I would like to conclude today's lecture, which has looked into various facets of Carbyne chemistry, and we are going to be looking at such a similar orbital interaction for the Schrock type Carbyne complex in the subsequent lecture, and compare its reactivity with that of the Fischer type ones we have discussed in this particular lecture. Along with that, we are going to look at various reactions of Carbynes that are unique to this moiety, and several other aspects of Carbyne chemistry will be the topic of next lecture. So, with that I thank you for being with me in this lecture, and I look forward to being with you in the next lecture. Thank you.